So you have scatter radiation, secondary radiation being produced up in the tube. You've got the primary beam interacting with the patient. Whatever's left, whatever remains of that is known as remnant radiation, correct? What's in that remnant radiation? You've got primary and what?
Scatter.
Scatter, okay? So the object of the grid is we want to employ a grid in between the patient and the image receptor so that scatter radiation, we're trying to minimize the amount of scatter radiation interacting with our image receptor. This is what the grid is for, as soon as my computer comes up. Why did it turn on?
Let's go back to the other one.
Yay. Okay, so here's my patient. Okay, primary beam, whatever's left is going to be primary and scatter. The grid, this is your grid, is going to be placed between the patient and your image receptor, like so. Okay, so anything, any scatter radiation interacts with the grid is going to be cleaned up and removed before it interacts with the image receptor. Okay, so with that said, what do you think is going to happen to our overall image once some of that scatter radiation is removed? What's going to happen to contrast?
It's gonna
Go down.
go up.
It's going to go up, right? Because we're removing the scatter radiation. What else is going to happen with our image?
It's gonna be less dense.
Okay, less dense, better contrast,
Good quality.
better quality. So you're going to have better resolution.
Is the grid, is that part of like the Bucky tray, or is that something?
Okay, so what I'm going to do, okay, so the question is this part of the Bucky tray. So the question, so this is what I'm doing, okay? What I'm going to do is I'm going to introduce to you two ways in which the grid is employed. One would be portably outside of the department, and the other one is actually built into the construction of the table, okay? But, so for intents and purposes, so you guys have a better understanding, I'm going to utilize the portable one for demonstration. Cinco de Mayo, huh? Everybody wants to leave. Yeah, I got plans too, so don't worry. I gotta be somewhere. All right, let's give it a few. All right, so the way these grids work is you have fine, very thin strips within the construction of the grid, very fine leaded strips going down the length of this grid right here. So it goes to the length of this grid, okay? Very fine lead strips. So what we're doing here in essence is that if I were looking at it this way, the lead strips will be going down just like this, okay? Very thinly spaced lead. Now, if I were to look at it in its cross section like this, the strips will be coming down this way. Okay? Now, as we know, here's your patient's body, here's your primary beam. Scatter radiation is going to go in all different directions. Okay? The purpose of the grid is to allow the more straight traveling scatter radiation and primary beam to reach our patient. So anything coming in a very steep angle is going to be absorbed by what?
Lead.
The lead strips. And anything that's more straight is going to go between the lead strips and interact with our film.
So it just gives them like fine slots for it to go down, right?
What's that?
It's like a slot. It's like a slot for like
This is
the
film.
X-ray to go
Yes,
down.
so they're lead slots.
Like what? That's so confusing. I was like, didn't you say the patient was above it?
Yeah, that's what I did. That's why I took him out. There's my patient right here. My film's down here.
Double X-ray.
Yeah. So that's what's happening there. All right, we're in business here. Good. So I just gave you guys a preview for free, no charge. Okay, so again, as a preview over here, the greater the field size, the greater the beam size. So not only are you increasing the size of the primary beam, but you're also increasing the amount of what?
Scatter radiation.
Scatter radiation reaching your image receptor. And as we know, scatter radiation is going to increase density and decrease your contrast. So we can control the size of the field using a beam limiting device. However, even with smaller beam sizes, when the beam interacts with the patient, scatter radiation is inevitable. It's going to happen. Okay, so what we want to do is we want to clean out the scatter radiation before it reaches the film. So decreasing the size of the field size and using filters will significantly decrease the amount of scatter radiation produced when photons interact with the patient. However, due to the patient's size, their composition, we have no control over that. Okay, so we are going to implement what's known as a grid. Remember, 50 to 90% of the density on your radiograph is a result of scatter radiation. This is what's going to give us our overall darkness on our film, 50 to 90%. Grids, the objective of the grid is to minimize the amount of scatter radiation coming from the patient before it reaches the image receptor. When used correctly, grids improve radiographic contrast by reducing the amount of scattered radiation reaching the IR. We all concluded that, right? It just looks better. It looks great. The grid is placed between the patient and the image receptor. Yes, Sydney, you are correct. You're correct. As the primary beam passes through the patient, many photons are scattered in many different directions. Here is that cross-section of the grid that I showed you. A grid allows the straighter photons, remnant radiation carrying the aerial image, which includes both the primary and scatter radiation, so the ones that are traveling in a more straight direction to interact with the film, and those that are traveling in a very angular direction is going to be absorbed by the lead strips. Okay, this is an example again of a grid, a cross-section of one. So the lead strips goes along with the length of the grid, so lead strips go through the length. And grids are going to be used for body parts greater than 10 centimeters. Remember what I said, the thicker the object, the more dense the object, more scatter radiation is going to be produced. So we wouldn't be using a grid for our hands, our wrists, our forearm, our elbow. We're talking about body parts that are greater than 10 centimeters in thickness, which means from your shoulders all the way down to your knees. So from your knee to your shoulders. Knee, femur, hip, pelvis, lumbar, thoracic, ribs, chest, abdomen, shoulder. You guys following? And then it gets thin right here, but then we get thick again up here. So we're going to use a grid for our skull.
So basically just like your extremities, you don't use.
Extremities, you don't need it. For thicker body parts, yes, you do. Okay? All right. Again, principles of the grid is to absorb any type of radiation or photons that is traveling in an angular direction. All right? So while scatter radiation increases density, using a grid will decrease it. Because remember, what is the percentage of density that is produced by scatter radiation?
50 to 90%.
50 to 90%. So if I'm employing a grid and it's absorbing that scatter radiation, what's going to happen to our overall density?
It's going to go down.
It's going to go down, making the image extremely light. So what we have to do here is, although the grid does us a good thing, we are going to lose some overall density. So when we are using a grid, we also have to bump up our technical factors. Okay? It's not much. Okay, it's not much. But when we're talking about a proper diagnosis versus something missed, okay, we are going to increase that risk slightly. Okay? So invented in 1913 by Gustav BUCKY, it is constructed with extremely thin, closely spaced lead strips placed vertically up and down or in a slant to match the beam divergence, okay, with radiolucent material in between each strip. Okay, it can be plastic, it can be aluminum, it can be some kind of fibrous material, but it's placed between the strips to keep the strips separated. The advantage is it increases contrast by reducing scatter radiation reaching the image receptor. However, the downside to this is because it is a radio-opaque material, those strips may show up on your radiograph, and this is known as grid lines. Grid lines is the physical manifestation of those lead strips on your radiograph. Okay? And because it is absorbing scatter radiation, we need to compensate for that loss of density by increasing our technical factors. Bless you. Which again, it is an increase, but it's very insignificant in the amount of dose that they are going to receive. So we're going to be talking about grid efficiency, and this describes the ability of the grid to absorb scatter radiation. We're going to discuss 2 physical and 3 functional factors about grid efficiency. So we'll be talking about grid ratio, grid frequency, and then we'll talk about selectivity, the K factor, or the contrast improvement factor, and then we'll also talk about the BUCKY factor. Grid ratio describes the height of the strips to the distance between them. Describes the height of the strips to the distance between them. It is our number one factor in us describing the grid's characteristic is a grid ratio. So here's an example of how do we find grid ratio. It is the height over the distance between them. So the height is 24 micrometers, and the distance between them with interstace material is 300 micrometers. Simple division. Our grid ratio is going to be 8 and written as a ratio 8 to 1. 8 to 1. Well, what does this number mean? The number means is the lower the number, the shorter, okay, the shorter the height of the strips, and they're also going to be more widely spaced. Okay, shorter and more widely spaced. In reverse, the greater the grid ratio, the better the grid efficiency. Why? Because now the strips are going to be taller, and they're also going to be closely spaced together. What's going to happen is the shorter the strip and the more widely spaced they are, those traveling in an angular, photons that are traveling in an angular direction has a greater chance of going through the strips. Okay? Now let's just take the same angle with a taller strip. What's going to happen with that same angle? There's a greater chance of it interacting with the lead strips. So in other words, you need a photon that's going to be more straight for it to go or bypass the lead strips. So something that has a 16:1 grid ratio has a better cleaning efficiency. A better cleaning efficiency than the one that is 8:1. So I'm going to be sharing with you the pros and cons here in just a moment. Grid frequency refers to the number of lead strips per centimeter or a given distance. Grid frequency plays a role in determining the thickness of the lead strips. The greater the frequency, the thinner the strips. Okay, let's just say this is 1 centimeter. Here is one grid, here is another grid. If I had thick strips, I can only accommodate a certain number of strips. So here I only have 1, 2, 3, 4, 5. 5, but they're thicker, right? If they're thinner, I can accommodate more strips. okay, but they're thinner. Okay, so let's just call this 20. 5 thick ones or 20 thin ones. All right, that's your grid frequency. Which of the two is better? Okay, if it's too thick, because the strips are thicker, what are you going to end up with on your radiograph?
Thick lines.
Grid lines. You're going to see the physical manifestation of the lead strips on your radiograph. Now, are we going to see grid lines with thinner strips? No. You guys agree? No, because they're thinner, right? But because they're thinner, what's going to happen with the stronger energy scatter radiation?
It's gonna go through it.
It's just going to go right through it. So there is greater chance of penetrating those strips. So what we want here is we want a happy medium. Here's that happy medium again. So we don't want anything too thick or too thin. However, we want it thick enough to attenuate the lead strips, but thin enough to avoid any type of grid lines. Okay? Therefore, low frequency grids again are going to be the most efficient than high frequency grids because they're going to be thick enough to absorb the scatter radiation, and they won't show up on your radiograph as grid lines. Okay? Here's an example of grid lines. You can actually see the physical manifestation again of the lead strips. Okay, grid efficiency. 3 factors: selectivity, the K factor, and the BUCKY factor. Very simple. So all selectivity means is being able to discriminate the primary radiation from the scatter radiation. Okay? Which has a better cleaning efficiency or better selectivity? A higher grid ratio or a lower grid ratio?
Lower grid?
Higher.
Higher grid ratio is
Oh,
going to
higher.
be more selective in removing the scatter radiation. Especially even like the minimal angular photons. They may be slightly straight, slightly angled, but it's going to clean up those angular scattered photons. So it's a higher selectivity. So higher grid ratios have a higher selectivity. Number 2 is the contrast improvement factor, which is going to give you better contrast, a lower grid ratio or a higher grid ratio, which is going to give you better contrast. Higher grid ratio because it's cleaning out more scatter radiation, which causes fog, which decreases contrast. So higher grid ratios has better selectivity, therefore it's going to give you higher K numbers, higher contrast improvement factor. Don't get yourself all wound up in this. Just the definition. So higher grid ratio is going to give you a higher K factor, higher contrast. Okay? Higher grid ratio is going to give you better contrast, a higher K factor. And then lastly, the BUCKY factor. Remember, when you employ a grid, it is going to clean up that 50 to 90% density on your image, right? So with that in mind, with a higher grid ratio, is it going to have better cleanup than a lower grid ratio? Is a higher grid ratio going to have better cleanup than a lower grid ratio?
Yeah.
Yes, it's going to absorb more scatter radiation. So because it absorbs more scatter radiation, we got to compensate for the loss of density here. So between an 8:1 and a 16:1 grid ratio, which of the two are we going to employ higher technical factors? A lower grid ratio or a higher grid ratio?
Lower?
Higher, yeah, well, it was 50-50, right? So it's going to be the higher grid ratio because it has a better efficiency of getting rid of scatter. It's also removing a lot of that density. So we got to use higher technical factors than you would a lower grid ratio.
So what would you adjust? Just the mass, basically?
Okay, so this is where the BUCKY factor comes in. Here's the BUCKY factor. Okay, we will adjust the mass because we're talking about a number of X-rays that are being absorbed, scattered X-rays. So we want to increase the number of x-rays that are being produced up at the tube. All right? So if you're going to be using a 5-to-1 grid, you're going to multiply your original mass by 2. If you're going to be using a 10-to-1 grid, you're going to multiply your original mass by 4. What the heck are you talking about, Dr. F? Okay? Well, let's just say, for example, I'm going to the emergency room. Okay, I'm going to the emergency room. In my department, I have a set of technical factors that I know will work each and every time without a grid. But now I'm going to be bringing my grid along with me to the emergency room or the operating room. Okay? Knowing what I know about my original technique that works in the department, I'm out of my department now. So what type of modification do I need to make with my technical factors to give me the proper density on my film? This is where the BUCKY factor comes in. Each of your grids will tell you what your grid ratio is. This one in particular is a 10-to-1 grid. So if I was using 70 kV at 5 mass for a chest x-ray in my department, I'm not going to go shoot this portably in the ICU or the OR in the ER. This is 10-to-1 grid ratio. How much should I increase my mass by? 4. By 4. When I multiply my original mass by 4, it'll give me the same exact density as if I were using the original technical factor in my department. Okay? Memorize this chart, guys, okay? So radiograph without a grid requires 110 kV at 2 mass. If a 16-to-1 grid is used, what would the new exposure factor be? What's your BUCKY factor for 16-to-1?
6.
6, right? So I'm going to multiply 6 with my original mass. My new technical factor will be 110 kV. That stays the same at 12 mass. Okay? Let's talk about the different types of stationary grids. We're talking about portable grids here. You've got your line, also known as your non-focus, also known as your parallel grid. They all mean the same thing. Linear, non-focus, or parallel. The next one is focused, and the last one is crossed hatch. The linear non-focus, the strips are straight vertical. Straight vertical. Okay? The strips go along the length of the grid. The length of the grid. The problem with this is that if you angle your X-ray tube a certain way, or if your imaging plate is angled a certain way, so let's just say now your X-ray is coming down in an angle instead of straight up and down. What are the chances of those beams interacting with your film?
Not good.
Not good, right? The new term I'm going to introduce you with here is what's known as grid cutoff. Grid cutoff is when the grid attenuates a portion of the primary beam. Grid cutoff occurs when it is absorbing or attenuating a portion of your primary beam. Not just your scatter radiation, but also your primary radiation. So if it's absorbing both scatter and primary radiation, what's going to happen to your overall image of your film?
It's going to be too light.
It's going to be too light. This is known as grid cutoff. Grid cutoff. Okay? So this can happen, and I'm going to show you guys this later on. This can happen when your tubes are not aligned right, if your image receptor isn't aligned right. Okay, so if your tube is angled, if your plate is angled, or your central ray should be directed where? Right in the center of my image receptor. So if my central ray was off-centered, okay, we're making a sandwich here where the bread, the meat, the lettuce, the tomatoes, and the other side of the bread are going to be stacked one on top of the other. They all have to be properly aligned or you're going to get grid cutoff. Okay? The next one here is a focus grid, which matches the divergence of your X-ray beam. Okay? The original peripheral cutoff, but you do have to be almost exact with your image SID. The last one here is your crosshatch. So you're going to have your longitudinal strips as well as cross strips. This is your crosshatch. Here, at least with the other grids, you have some room of mistake, but with crosshatch, you cannot make any mistakes. Plain and simple. Everything has to be aligned one on top of the other with no angulation of your X-ray tube or even your image receptor. Otherwise, you're going to have grid cutoff. Okay. Now let's talk about the moving grid. This is one that's actually built into our X-ray table. Okay. You've heard of me talking about the film tray. It's hard for me to say film tray because I'm used to calling it BUCKY. Your BUCKY is the film tray. Okay? I just don't say, I say film tray so you guys have a better understanding of where your image receptor is going. It's going into your film tray or your cassette tray, but it's also known as your BUCKY. It's your BUCKY grid, your BUCKY diaphragm, or your Potter BUCKY diaphragm. This is what's built into your X-ray equipment inside the rooms. The advantage of the moving grid is that during exposure, the grid moves during exposure. What is it doing while moving when it's moving during the exposure? What am I eliminating?
Scatter radiation.
Blurred lines. You know that's not right. It's eliminating the blurred lines. Okay, that you would usually get with a stationary grid. So if it's moving during exposure, it's getting blurry. We're eliminating the grid lines. Okay? So let's talk about how these moving grids work. There's three different types. You have the single stroke, which means that during exposure, it's going to sweep across the table during the exposure. Okay? However, before I can make a next exposure, I've got to put it back into start position. Okay? That's your single stroke. Shortest time available is 1/20th of a second. Anything faster than that, it's going to be inefficient. It's not going to work properly. Reciprocating grid, okay, extra step. It goes across during the exposure. After exposure, it automatically comes back into start position. Shortest time of 1/60th. Anything shorter than that, it's not going to work properly. Oscillating is what you will find in most of our modern day equipment. It's oscillating. So it doesn't just move across the table, it's going to go in all four different directions. A sweeping motion. That's going to be the most efficient. Okay? Shortest times of 1/120th or less. That's what's going to happen there. Okay? Any questions on the moving grids? Okay, what's grid cutoff? We just talked about that. Not only is your grid absorbing scattered radiation, but what else is it absorbing? Your primary beam, your primary radiation. Okay? We're going to be talking about, this is going to be quick, guys, so hang in there. Your SID, your angulation, your centering, your upside down grid, and also your parallel grid. Now, with okay, here's an example of a grid cutoff. You got perfect density in the middle, but then it's absorbing the primary radiation on the sides. Again, this can change with angulation of your beam, angulation of your grid. It can be that your beam is not centered to the grid. These are just some examples. Okay, your SID or off focus error. In each of your grids, you are given what is known as a grid radius. This is what the manufacturer says will be optimal for your grid to work, is at distances of 40 inches. Okay? So you're going to use your SID of 40 inch. However, again, you may end up in the ER, OR, ICU, where you're not going to have that type of freedom. You're going to have some limitations. So you may not be able to get your 40 inches. Okay? So what is my range of error? What is my margin of error? Well, this is where your focal range comes in. So they'll say, okay, well, if you can't get 40, as long as you're between 34 and 44, you should be fine. If you have anything less than 34 or greater than 44, you're going to have what?
Grid cutoff.
Grid cutoff, okay? And with this type of error, with your SID error, you're going to have peripheral grid cutoff. So you're going to have loss of density on the periphery of your image.